So here I've got a helium atom right here. And so if we take just the individual weights of that helium atom, we get this calculation. So you get the 2 protons, 2 neutrons, 2 electrons, and they all weigh these weights here. So 2 times 1.007, 2.1.008, 665, and 2 times 0.000548, and so you combine them together, you get 4.03 2979U.
Yeah, just before you go on that, just take note on that the neutron, look at the proton and neutron actual mass. They're about the same, but the neutron's just a tad heavier, right? And then, well, how does the electron compare?
It's like
Yes, it's way, way less. So it has mass, but it's so little we don't figure it in. Okay, so just, you don't have to know those numbers. I just kind of want you to see that protons and neutrons are about the same. A neutron's just a tad heavier.
So we have this number 4.032, and that's our total combined mass of our 2 protons, 2 neutrons, 2 electrons. What's the atomic mass of helium, just out of the blue? We see from
4.00260.
Right? So is this bigger or smaller than our total combined mass of the different particles? Smaller, right? And that again lines up with our mass defect, where the sum of the parts of the atom are going to be more than the actual atom itself, right? So, I guess, is it on here? Yeah, it's on here. So measure mass 4.0016 is 0.030377U less than the combined mass, right? So as far as the calculation goes, we can calculate the nuclear binding energy by basically taking that difference, right? So let me go back up here to make sure we have that number here. So basically we're asking, where does the rest of that mass go? And it goes into what? It should be from your notes. So where does the rest of the mass contribute? That like missing mass that we're not seeing in the atom itself. It becomes energy, right? So the second question is, okay, how do we know how much energy that is, right? And so this is where Einstein comes in. We finally get to talk about Einstein. He's everywhere in this classroom. He's right there watching us. And now we get to actually talk about him and why. One of the ways he's contributed to chemistry. So, where did my thing go? So, do y'all remember what Einstein's formula is? It's on here, but I mean, it's pretty common, right? E equals mc squared. All right, what does E stand for?
Energy.
Energy. What does M stand for?
Mass.
What about C?
Speed of light.
Speed of light, right? So we can use this calculation to figure out the nuclear binding energy of helium. So all it is essentially plug and chug, right? We want to find energy. We have our mass, which is our 0.030377 AMUs. And then we have our speed of light, which I guess this one is, oh, we converted to kilograms first. Okay, gotcha, that's what he did, okay. I was confused with the calculation at first, but yeah, so basically what he did first, just to make it easier on us, because we usually use grams rather than AMUs, if you remember that conversion, we mentioned it a while in chapter 3, with conversion being 1.66 times 10 to the 24th grams is 1 AMU. Do y'all remember that from, or remember at least me talking about that? You didn't have to know it, but it was just something that I mentioned. So that's why he used, or they converted into kilograms, which basically just, you know, adding 3 more negative to kind of get it into kilograms. So he converted it to kilograms right here, 5.0441 times 10 to the 29 kilograms. And then from there, you just plugged it in, right? Because we're trying to find energy. We have energy right here. We have our mass, which we plugged in right here. Our speed of light, squared right here. And then if you do the final calculations, you multiply them together, you end up getting this 4.54 times 10 to the negative 12 joules. Now, I don't think we've introduced the joule yet to y'all at all. But let's go ahead and make our own definition, right? So let's talk about these units here. So what's the units on the mass that we're using?
Kilograms.
Kilograms. What's the unit that we're using on the speed of light?
Meters per second.
Meters per second, right? But what are we doing to the speed of light?
Square.
So in the final calculation, what do we get?
Kilograms times meter per second squared.
So times meters normal or meters squared? Squaring both, right? So that's why we have this kilograms meters squared times seconds, or meters squared by seconds squared. And that ends up making our unit for the joule. So you'll see the joule a lot, especially later on when we start talking about energy. We use the joule as our unit for energy. So we'll talk about it when we get into enthalpy, which will be honestly much further on, I think. We still got a lot to go. We might not even get to it till next year. Next year, like as in February, not like not in this class. So that's something to keep in mind here, and something you might want to write down just to memorize, and just to kind of recognize. So if you see these units, you'd be like, oh, that's a joule. I don't have to write. I can just convert it directly. So 1 kilogram meters squared over seconds squared equal to 1 joule. So that's just kind of explaining how we can do these calculations with E equals MC squared. I don't know if we have a practice problem for just calculating this on your own, but you could theoretically calculate this for anything for energy. It's just, again, the same process that we showed earlier, right? Where it's like you want to find the mass of a proton, how many protons you got. Find the mass of a neutron, how many neutrons you have. And then find the mass of an electron, how many electrons you have. Adding them all together, then taking the difference between that and our average atomic mass, right? And then finally we can use that difference in E equals MC squared in order to figure out the energy of our nuclear bonding machine. Yeah.
Okay, so the 1.6605 number, that's what?
This is the conversion from AMUs to kilograms.
Okay.
So usually for joules, like we said, we use kilograms for joules. We can actually, honestly, do we want to just do a calculation of nuclear binding energy just with a different?
Yeah. Remember, we're an MKS system, meters, kilograms, seconds, that those are the fundamental units on the metric system. So anytime you plug it into an equation, mass has to be in kilograms, length has to be in meters, time has to be in seconds. Okay? And so that's why we have to convert AMUs to kilograms. Now, you would never have to memorize this. Okay, that's always going to be given to you, just like all the other conversion factors were given to you. But you need to be able to set it up. But again, since atomic mass units is on top, it goes on bottom, and we just multiply, so that gives you how many kilograms. Okay? So if we want to do a practice problem, okay, just blank the screen.
Oh yeah, but
And I'll let you take them through it.
Yeah.
I just looked one up.
just want
Okay?
fair enough.
Uranium 236. Okay? And if you went through it, uranium, if it's 236, I'll write it this way. How many protons does it have? Okay? Actually, let's say, I think it's going to be uranium 235. Okay? It's got 92 protons. How many neutrons? How do we figure out neutrons? Subtract, right? Okay? So whatever that turned out to be, what is, I think it's 143. Okay? So we could add up and get all the individual weights, but let's just say, okay, we know that this atom weighs 235.0349 AMUs. I write AMUs, they're used U in the book. Okay? But the sum of the parts is equal to 236.0349 AMUs. So this is the actual mass of the atom. This is what, if you took the 92 protons, the 143 neutrons, and the electrons, they would all add up to this. Is everybody with that? Okay, so how do we do, what is the nuclear mass effect? And then how do we convert that? Why don't you take a couple of minutes and see if you can do it based upon that example that he just did?
So, again, nuclear mass effect, just think, how do we solve for the nuclear mass effect? And then the second part, just finding the energy, remembering E equals mc squared. How do we get to the, do we have a conversion? What's the conversion factor?
1.66
Yeah.
times.
What is your 1.66, yeah?
Times 10 to the minus, I think it's 27.
Yep.
Equals 1. So there's the conversion factor between AMUs and kilograms.
Okay, so on this one, we just put these numbers in the calculator, and then we do it, like for the example,
Okay.
we just put those in the calculator.
Yep.
And then we just kilograms times meters squared, and then that, second squared.
Yeah, and then that equal, and then you can just convert it to, yeah, you can convert it to joules. And make sure it's capital J, because
Okay.
just to make, keep it in line with joules. I don't think, I feel like there was something that used lowercase j somewhere in science. But I don't remember what it is, and I don't think we talked about it in chemistry. I think it might be a physics thing. I think it's like the jerk name. Uses lowercase j, is there anything that uses lowercase j? I can't remember.
Use what?
Lowercase j as a unit?
Oh.
I feel like it's something in the title of things. So, I mean, we don't use it, but to keep us standard with scientific standards, you make sure to use capital J when we're talking about joules, all right? Plus, it's named after somebody. Named after somebody's last name Joules, right? We don't want to disrespect him.
James Prescott Joule.
James Prescott Joule. I don't want to disrespect him. It's like, what if I wrote your last name in lowercase? You probably wouldn't care too much. You'd be a little mad, but.
Yeah, well, I mean, I forgot that we haven't gotten to this.
Yeah, it's okay.
If you can get to the first, you know, if you can go fast.
Wait, what's the speed of light then?
Exactly.
3.00 times 10 to the 8.
I mean, hopefully should we do that.
Wait, where'd you get that?
Where'd you get the numbers?
Write it down.
Yeah, but that was like the math.
Oh wait, yeah, never mind.
We should just have.
Did I not scan? I showed you the virtual fields.
Where are we? Oh, you don't know where to start? So, what's the definition of redoing the mass effect? Right here. You know.
Trying to calculate the nuclear binding energy. So you gotta find the mass effect, and then you
So
gotta
we're going to try
convert
to
that
find that. What should we do?
to energy using E equals mc squared.
Subtract
Okay.
that.
Yeah. So, well,
And then you put it.
yeah, because that's the mass we're looking for the energy, right? Because where does
Did you get like
the missing mass
150
go into?
something?
We just talked about it. Yeah, the missing mass goes into energy. So basically, we get to find what the energy is.
Wait, when you multiplied that, the speed of light and the mass?
Okay, so, oh, you don't have the first two notes, right? Okay, so the nuclear mass effect, you kind of briefly said it, but do you remember what we talked about?
Oh, the difference between those two numbers. So subtract those. You use the difference for like.
Yeah, because the rest gets converted into energy, right? So if we're trying to find the nuclear mass effect of uranium-235, right? So we have the sum of the parts, we have the atomic mass of uranium-235. So how do we find the nuclear mass effect?
I don't think I'm doing it
I don't even know where
right.
to start.
Yep, so you subtract it, yep.
I get 150.
So, It'd be like
What?
1 inch. Well, 1 inch, right? Because some of the parts are always going to be bigger than the atom itself, right? So you want to make sure you subtract the bigger number here. And then from there, you want, okay, from there, we use E equals MC
Are
squared,
you doing
right?
math?
We're trying to find E.
I know. I forgot how to
We know what the
fold.
speed of light is.
Look one.
I should put the
I
speed of
know.
light
I
up.
was doing it in the different.
I'm going to put the speed of light up real quick.
0.03 is the difference.
So do you
And
square that, then you won't
So
find
this
it.
is on.
Here, let me put the speed of light up. It's
Wait, I
3.
think I did it wrong.
3.00 times 10 to the 8th.
Wait, you subtract that mass and then put it in kilograms?
I would. I wouldn't really want to calculate both of these in kilograms, right?
Yeah.
The only reason we need kilograms is we're trying to find energy,
Yeah, I
right?
forgot to subtract. That's why I did it wrong.
Gotcha. Yeah, because again, we're talking about nuclear mass effect. You're looking at the definition of nuclear mass effect, and you're like, okay, so I'll just do what the definition tells me to do, and then plug it into our energy formula.
So it's just gonna be that number.
Let me double check. Okay, well, not crazy. Speed of light. There you go. The speed of light. Any place that you're confused about? Okay. What is the nuclear mass effect? Define it for me.
Difference in mass between the individual particles and the actual mass of the atom.
Okay. So, do we have the mass of the atom?
We're doing which one?
With this one right here, the uranium, right?
So that'd be 2.5. Wait, no.
Okay, so that's the average atomic mass. Remember, we gave you the specific mass of uranium-235, right? And what is it?
235.
All right. Do we have the sum of the parts?
So,
Yeah. The sum of the
Wait,
parts.
I need to see it.
Blank. Oh.
All right. So how do we find the nuclear mass effect?
Okay, what?
It is the
I got
difference between the
1.5.
masses.
Just try.
Yep. Yep.
Oh.
And now you have the nuclear mass effect. And then how do we use the nuclear mass effect to find energy?
I was thinking to.
Am I gonna finish?
Yeah, exactly. Sometimes you just think too much on these problems.
I
It
forgot how to
happens.
foil.
So would this be an AMU or just?
I know.
So we want AMU, right? And then we get to kilograms. Right? So how
I
do
spent
we
my whole
convert from
freaking
there to
day
kilograms?
So
Finish
you
this.
do the 1.66.
Uh-huh.
0.
Fine. I was doing, I don't know. I'm good now. I was doing this like Spanish project
Okay.
Yeah,
late last
and
night.
now you got it in
She
math,
assigned
and
it
then now
last
you gotta
week
plug it
and it
into
was
the
due
formula, right?
tonight.
So
Definitely
what is
finished
this?
it.
What do we do with
Or
that?
started at 8:30.
So we have the math, right?
That's this number right here.
So that's good, right?
The number.
So that's from the example. So this is the nuclear mass effect of helium.
So
The
for
example.
this, it'd just be 1 since for the uranium.
Yeah. So it's 1. We did the same thing here, and then now you just gotta find the energy, right? And we use the formula equals MC squared, right?
So then you just take that up, multiply it,
Great.
Yep. Speed of light.
which is 3.
Yes, it's a problem.
Yep. And then that equals.
Oh yes, love the bun.
Huh?
Well, I'm tired of wearing my hair now.
Yeah,
Give me like 1 more minute.
I didn't wash my hair last night, so it's not
We'll
here.
go over it and it'll make sense.
we'll put them all in practice for these.
See, Mr. Hobbs looked up this example online, so I don't know the actual answer, but if we work it out, we'll get to the right answer. So,
Ew.
Eventually.
eventually, it won't be too bad. I think this is a pretty nice problem. I think that's why it's, especially with finding the nuclear mass effect. The nuclear mass effect
Finish my marriage.
is,
So this stuff will always be given to us.
Good job.
yeah, you will not have to try to look
Until
up.
you literally.
So what you might have to do in a
Wait,
problem
why is that
is calculate
perfect?
the sum of the parts, like, but we'll give you the mass of the proton mass and the neutron mass and the electron. So you just have to multiply and so to find the sum of the parts.
I know, I'm so
But that's the only
sorry.
other extra thing that we probably do in our studies. All right, let's go through this. So, nuclear mass effect. That's an M. Nuclear. Defense. What is the nuclear mass defect? Who can tell me?
What we lose during like, when
The
they
difference in
combine.
mass between the individual parts.
Okay, so what's the difference between the mass, some of the parts, and the
One.
one? Yeah, there you go.
Yeah.
236.0349 minus 235.0349 equals 1 AMU. Right?
What AMU?
So, how do we
AMU.
find the energies of this nuclear mass effect, the nuclear binding energy here?
You convert it to kilograms.
Convert to kilograms. How do I convert to kilograms?
Multiply it by that number.
I'm assuming by that number you mean this number right here,
Yes.
right? Alright, 1 AMU. I'm not even gonna, I mean, if you can multiply 1 by 1.66, it's gonna be 1.66.
What is that? No.
1 AMU times 1.66 times 10 to the negative 27 is gonna be 1.66 times 10 to the negative 27. Make sense?
Do we have to write that out, or is it,
Yes,
can we
I
just
got
like
that.
imply it?
I mean, as long as you show your work up to that point and I can understand that you converted it, it's just that this one's really easy, right? But let's say you've got not 1 AMU, but like maybe like 0.594, right? Then you probably want to show your work just to keep your work in track, so you can kind of show me this is how I got to kilograms, this is how I converted it. Because this one's easy, obviously, because you're multiplying by 1. But, you know, you're not always going to be multiplying by 1. So we have kilograms, right? And then where do we plug the kilograms into?
Plug in the mass UMC squared.
Equals MC squared, right? So where do we plug it in?
Mass.
Mass, right? So we have E, we're trying to find E, equals 1.66 times 10 to the 27 kilograms times what?
3.00 times 10 to the 8 squared.
10 to the 8th what?
Squared.
What's the
Oh,
units?
meters a second.
Meters per second. Yeah, there you go. Square it all. And we'll get our energy. What did y'all get for energy when you did this calculation?
1.49?
Oh yeah, I got that too. 1
I
point.
got 4.98.
So
But I rounded it to 1.5.
Okay.
1 point. So let's think about this for a second, right? We're multiplying a 1.66 times a 3. Are we gonna get 1.5, or are we gonna get something closer to 4? 4,
Wow.
right? So you got what?
4.98 times 10 to the negative 19.
Wait.
4.98 times to the negative 19th. Did anybody else get that?
No, I just got 1.49.
Let me get a calculator out.
And then it was like times 10 to the negative 10th.
Yeah.
Let me see what the calculator says. Alright, so 1.66
Some mountains over missing. And it's
times
like
10 to
if their class was like way too big, they have to go in the hall.
Yeah, because.
I was like, what?
My class is stayed small.
Yeah, my math class is pretty big.
My
But
biggest
that's
class
what
is like English.
Oh, my English class is so small.
Oh, I see what happened. Duh, I'm not thinking squared. Duh. Duh, 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 duh.
Oh!
Yeah, that's what happened here is I'm not thinking. So we got 1.49 times 10 to the negative 10th.
Yes, we did.
I know
Yeah,
I'm
okay.
a button.
Right?
That's on me too. I was.
Did we do it? Did we do it?
Yeah, we're not just multiplying by 3. We're multiplying by
Super, we did it.
9 with a whole lot
That's
more.
your paper, just the-
Yeah, so you got about 1.5. So I'd say with sig figs rounded to 1.49 times 10 to the negative 10. What's the unit?
Joules.
Joules.
Yeah.
Awesome.
Okay, so how do we go to kilojoules?
What?
Multiply it by 1,000.
Multiply by 1,000?
Divide by it.
Divide by
Divide by
1,000.
So what does that look like
means
then?
1.49 times 10 to the minus 13
13.
kilojoules. Now, what we like to do with nuclear binding energy is do it per nucleon. Does anybody remember what the definition of a nucleon is? First page of those notes. What's a nucleon?
Nuclei?
Nucleon.
Oh. More.
It's on this
Binding
somewhere.
energy.
I don't think it's on here, actually.
Nucleons are all particles in the nucleus. Basically, it's the mass number. So in this case, we divide by 235. So you go kilojoules and then divide that by 235, and that gives you the binding energy per nucleon. Then you can compare that with the stability. Okay? So a nucleon is total, any particle in the nucleus, but really there's hundreds of particles in the nucleus, but we just really focus on protons and neutrons. Okay? And then, so you just get joules to kilojoules by dividing by 1,000, then divide by the mass number. And kilojoules per nucleon.
What is that 10 to the power of? In like your answer?
Oh, this is 13, sorry, it looks like a B. And it's 10 to the 13th, right? We got 10 to the 10th joules, and we converted it to kilojoules, which put us at 13, and then
Kilojoules per nucleon?
Kilojoules per nucleon. Kilojoules divided by nucleon.
say nucleon would be named like I'm not actually ever done this calculation.
Huh?
but-
It'd just be like KJ.
Yeah, like what it's up there. Lowercase k, capital J.
Okay, so this shows the binding energy per
What?
nucleon of all the different elements. Notice that the greatest binding energy is right up here at iron. That means it's the most stable nucleus of all. Okay? These are too small. This is just right, and then it just starts going down as you get bigger and bigger.
Oh, they go by pole, that makes sense. That makes sense.
Thank you.
Yeah. They're doing it kilojoules. We did it just kilojoules per nucleon. They did it kilojoules per mole per nucleon. Okay? What we did is individual atoms. How do we convert it to moles? What number?
The
This
6 point.
number is all we have to
They just
include to go to moles.
Right?
Okay, but you're not, I mean, you just kind of need to know the definition, and you should be able to do just a basic calculation on that, okay? Nothing basic.
Yeah, and I know we're using a lot of words like nuclear and mass effect and all that, but really I think it can be very tempting to overthink these calculations, but really it's just finding what you need and plug and chug. It's just understanding where you need to plug and chug, I guess, is the big thing on that. Okay, so I'm going to go into the 6 types of radiation.
Like the Pretty Little Liars thing.
So,
Got a secret. I want to watch that show.
No, you can just, no, you can just get rid of the book. I'll
Wait,
just
what?
get it out of the way.
yeah,
Oh. Yeah, I want to watch
Okay,
it, but I
so I know in the video we already talked about alpha radiation, so we'll kind of, or alpha decay, so we'll kind of just quickly go through this one here. So alpha decay, what does it consist of? What particles does alpha decay?
Oh, wasn't it protons?
Two protons, 2 neutrons.
Two protons, 2 neutrons. Here, let me do this so I can fill the notes with y'all. There you go.
I just
Yeah, that's
want
straight
to
from the
sing
video.
hopefully
It's the 2 protons and 2 neutrons. Where's all this here? So we call that an alpha particle, but it's important to know what makes up an alpha particle, right? It just so when we write that, we get we basically write it as a helium atom because technically it's the nucleus of a helium ion. If you just take again kind of what all elements are basically grabbing a bunch of protons, grabbing a bunch of neutrons, putting them together, and then wrapping them around with electrons, right? So you can make any number of elements just with that. Obviously, it's the actual process of making it is a lot more complicated than just grabbing some protons and grabbing some neutrons, right? But in a sense, all elements are based on that. So for a nuclear symbol, they write it like this, and they explained in the video why they write it like that and why it doesn't have a charge and whatnot. And that's just because with nuclear equations, we're just trying to figure out what's going on in the nucleus. So it's different than what we were doing when we were writing out the atomic symbol from like the test. You remember where you had like the oxygen, there's a mass number, on top number bottom, and the charge over here. So this is different than that because we're really just worried about the nucleus on this one. Right? So if it's 2 protons, 2 neutrons, what charge does this thing have?
Positive.
Positive, right? Alright, so it's the biggest, slowest, and least penetrating type of all types of radiation. What can this be stopped by?
Paper.
It can be paper, it can be skin. Pretty much anything can stop it, which is a good thing for us if it's not inside our bodies, but if it's inside our bodies, it's a very, very bad thing. I think one of y'all did polonium, right? And so that's one of the, for your elements, that's one of the reasons why polonium can be so toxic. So polonium, the radiation that it emits is alpha particles. So it's not dangerous when it's outside your body. Once it gets inside your body, it can't leave your body, which means it just bounces around inside.
Oh.
Yep. So part E, I believe part E is just referring to what kind of isotopes do we think alpha emitters might be? Do you think they'd be stable or they'd be unstable?
Stabler but unstable.
Stable or unstable?
Like it's the most stable.
The stable of the unstable.
Yeah,
Like the most
stable.
stable.
Get out your periodic tables.
Yeah.
You have the color periodic tables. Look at the top of the selected radioactive isotopes. It gives you the type of emitter, whether it's alpha, beta, or gamma. Where are your alpha emitters mainly?
Way up.
Find random
The
things.
heavier ones.
Yeah.
Oh, you don't have one of the periodic tables, I think?
From 2.
This is the right one?
Yeah,
Oh, no, this one looks like the one you gave me. P. It's the same.
the same one.
Here you go.
What does it say? Does it say alpha on it?
It should be the little like fish looking thing.
Yeah.
What?
Or an A.
Wait, where would it be?
Looks like this. Yeah. Oh, so y'all didn't get periodic tables in general. Oh.
Are you sure?
No, we have them in our binder.
No.
I think the other half.
The other half of us didn't get it.
Yeah, exactly right. We're the best
I
class.
asked before and everybody said they got one.
I'm really confused. Where do y'all see that fish thing?
Look, it's the A. It's just an A.
Where?
It's really tiny.
No. Okay. There you go.
Oh, it's on that part. I thought it was a lot of stuff.
So yeah, actually that is my bad, because it's not necessarily.
Okay, how is that supposed to find that? I
Right?
don't know.
So you don't see them with. You wouldn't see them with like radioactive isotopes of some of the smaller elements, right? Because again, you're getting rid of a full helium, right? Some of those small elements can't afford getting rid of 2 protons and 2 neutrons as they emit. So generally the larger ones, which is also generally the larger ones is when you get unstable. I think we mentioned the notes that past a certain number, it was all the elements past a certain number are going to be radioactive. Y'all remember that? Or is that
It was like 83 and on or something.
83? Yeah, something. I think it was 83, right? Because yeah, that makes sense. I'm trying to look at the periodic table that makes sense. Yeah. So and it makes sense for the half particles here. So so let's look at the examples here of how to write these equations. So which is weird because the notes are up here. Basically, it's just with when we're doing these nuclear equations, we're just solving kind of a math problem. We're going to be missing something. We know what kind of radiation is, and we're just going to write out what happens to this molecule, right? So in this first example, we've got uranium-238. We know it undergoes alpha radiation, or alpha decay, and we end up getting this helium nucleus plus, I think it's thorium or thallium, I can't remember. Thorium, yeah. Thorium-234. Right? Does that make sense? So now let's try to do this next one. All right, so we've got 208 polonium here, and it goes through alpha radiation, right? So what are we going to get for here?
2, 4, and then 8.
2,4 He. So our helium
Oh,
nucleus, right?
Wait, would it always be a helium nucleus first?
I mean, as long as you make sure that you know it's split up, it doesn't necessarily matter, but I like to write it with the radiation first. Some of the problems in here doesn't write the radiation first, I don't think,
It
yeah.
doesn't matter, it's just like addition,
Yeah.
the order doesn't matter.
Okay.
So it doesn't necessarily matter, it's just, I think I'm more comfortable writing it like this, but, the problems that you'll be given aren't necessarily gonna have this first. So a helium, nucleus, and then if we look at our periodic table real quick, we're gonna find polonium. So I found it right here, because we're looking at number 84. And, yeah, it turns into lead, I did hear that. So, what's the atomic number of lead? 82, right? And then what are we gonna have for the mass number here?
204.
204. And then symbol for lead? PB. Awesome.
Because
So
you have
find polonium.
helium, so then you subtract it from the.
Okay.
Yeah, exactly. So basically you find, you know what your number, your atomic number is for polonium. You know that you're losing 2 protons, so it has to change to a different element, right? So we just look at the element that has 2 less protons, and that's going to be lead. That makes sense?
Wait, so alpha is always going to be losing the 2?
Yeah, alpha, this is how alpha radiation is always going to look like. You're always losing a helium nucleus, and then your nucleus is going to be changing, right? So they kind of mention this in the video too, right? Normally with reactions, which we haven't necessarily got to the details of that yet, you know, you're usually like distributing electrons, you're moving around electrons, but with nuclear chemistry, we're messing with the elements itself. So that's why, again, that's why we also just mainly kind of talk about what's happening as the nucleuses, because those kind of matter more when we're talking about nuclear chemistry. This one make sense? Alpha radiation? Alpha decay? Alright. So,
Yeah, or larger.
very fine notes for beta decay, so I can show. There we go. Where's my color notes? There we go. So we're going to kind of define beta decay. This is kind of going to be, because it's just completely fill in the blank, it's going to be a bit harder to kind of decipher this one, but I'll help fill it in for y'all. So let's just talk about beta decay. Do y'all remember what happens to the particles in the beta decay from the video?
Like the electron is out of the shell.
The electron, so it somewhat does electron, but remember we're dealing with the nucleus, right? So something happens with the nucleus with beta decay. So it doesn't necessarily lose in a neutron. So basically you're right where you do have an electron that emitted, but something happens to that neutron. So basically with beta decay, a neutron is converted into a proton and an electron. And then you're right, I think Keith said it, I can't remember if Keith or Cooper said it, but that electron then gets emitted from the atom itself. So the emission here for beta emission is that electron, but the reason it happens is because a neutron ends up getting converted into a proton and an electron. Does that make sense? I mean, the process of this happening probably doesn't make too much sense, like how does a neutron do that, but just with radiation and how it works.
Okay, I've got 1 minute, let me just, a Hobbes definition, not a physics definition, a Hobbes definition is that a neutron is composed of a proton and an electron. Positive and negative together, come together and make a neutron. Therefore, the neutron's a little bit heavier than the proton. Trouble in paradise during beta decay, they split up, the proton gets to keep the house, the electron gets kicked out. Okay? Physics, like a physics definition is that the neutron undergoes just this energy spontaneous Superman in a phone booth, changes into a proton, and the energy that's given off just creates an electron that's emitted. My definition is much easier.
Yeah, I think I'm about physics. Nuclear chemistry is weird. It's super funky because it's kind of breaking some of the rules that we've kind of learned already, but it's just learning why those are around and why nuclear chemistry is.